Hello friends, today we will take up tutorial 9, which is the last tutorial in the series of tutorials in this particular online course. We shall deal with problems on multi-user CDMA. As the first problem, let us consider a code division multiple access scheme, and there are 4 users A to D with allocated spreading codes. So the spreading codes are pre-allocated. As you can see, they are distinct codes. I am not making any comments on the nature of these codes. These are just randomly picked up just in order to illustrate this problem, but these are not PN sequences or any such code which has been specially designed. These are just in order to highlight that we shall take some data bit and we shall process the data bit with this spreading code in order to realize our spreading signal. The important thing here is that we have 4 users, so it's a multi-user system, and we assume that we have transmitted symbols which correspond to bits 1 and 0 binary. For A, B and C, these transmitted bits are A equal to 1, B equal to 0 and C equal to 1. So essentially what the problem states is that if we have a bit 1 transmitted by user A, it is going to be spread with the corresponding code of user A, which is 8-bit sequence, as you can see here. B transmits a bit 0 with another 8-bit sequence, and C transmits a bit 1 with the corresponding 8-bit sequence shown over here. Some assumptions to start with: we assume that all the stations are perfectly synchronized, which is a debatable assumption because usually CDMA transmission is synchronous in nature. However, for the sake of simplicity, we shall assume that all stations transmit at the same time, and at the receiver, the received signals from these stations are also synchronized. Secondly, we assume that all cores are pairwise orthogonal. We also make another assumption that if these stations transmit simultaneously, which is what is going to happen in our problem, then the signals, that is the binary bits, are going to be mapped using a bipolar signaling scheme, and these bipolar signals add up linearly to form a composite signal which is received at the receiver, and then we use the despreading procedure in order to decode the bit at the receiver from a given user. So as I said, the bipolar scheme, signaling scheme that we assume is that binary 0 is mapped to a -1 and a binary 1 mapped to a +1 signal level. The transmitted signal, which is the linear combination or addition of the 3 signals, are given as shown. Now what is to be noted is how we obtain this is that this first row here corresponds to the bit 1 which was transmitted by A, which is mapped to +1, and this +1 is multiplied to the sequence, code sequence corresponding to A. So I'll just quickly show you how we obtain this. So this is obtained by taking this A signal by A, which is +1, and we have merely multiplied it with the sequence corresponding to this A, which is nothing but -1, -1, -1, yeah, +1, +1, -1, plus 1 and plus 1. So this multiplication yields this first row. So in a similar manner we can obtain the signal, spread signal due to B, which is now 0 multiplied with the code sequence of B. So in effect, since 0 gets mapped to minus 1, so what we are going to do is this 0 is a minus 1 and this is going to be mapped or rather multiplied to the code sequence, that is the bipolar code sequence of B. So since we are multiplying it with minus 1, effectively the resultant sequence is nothing but the inversion of this B, because this B is being multiplied by minus 1. So that's why we have denoted it by B complement, or here the complement sign basically means that we are inverting every bit and then mapping it to the bipolar equivalent. C is 1, so 1 multiplied by the code gives you the code itself, just like A. So once this is done, these signals, as I said, are synchronized and add up linearly. So the linear addition of signal levels is given by this row. So this is nothing but our composite signal at the receiver. So now we assume that the signal has been received as it is and noise has not corrupted the signal. So in normally what happens is we usually assume that there is going to be some kind of additive white Gaussian noise, but in this case we neglect the white Gaussian noise, additive white Gaussian noise, or for that matter any interference, and we assume that the composite signal is received as it is. So the way to decode what station C has transmitted is to take the inner product by representing this in a vector form, as you can see, and merely take the inner product of this received composite vector with the code vector corresponding to C. So and we scale it by 1 by 8 because that is the length of the code. So the inner product is nothing but element wise multiplication of the two vectors, or component wise multiplication, and then summing the result. 1 by 8, as I said, is the scaling factor, and as you can see, keep multiplying element by element and note down the result, sum up all the resultant inner product terms, scale it by 8, and we get plus 1, which can be mapped back to binary 1, which was the bit that was precisely transmitted by user of station C. So you can repeat this example by choosing to find out or decode what station B has transmitted, for example. So all you need to do is once again take the composite signal and this time multiply it by the code of B. So just remember that although B was 0, and in order to represent the spread signal we had used the inversion or complement sign. While multiplying the composite signal, we have to multiply it not with the complement but only with the original code B, because that is what is available at the receiver. The receiver doesn't know what the transmitter had sent, so all it has is are the codes A, B, C and D, and so multiply the signal with B and you will get back -1. You can verify that separately. D, user D, of course, in this problem has been used as a dummy. It basically has no role to play in the sense that we don't assume that it is transmitting. So this is kind of a silent station. So I hope you got an idea of what basic idea of what multi-user CDMA transmission is. Now let's proceed to the second problem. So in the second problem, we have a CDMA system which uses direct sequence modulation. We have a data bandwidth of 10 kilohertz and a spread spectrum bandwidth of 10 megahertz. Now, if only one signal were to be transmitted, then we have EB by N naught metric at the receiver, and that is specified to be 16 dB. However, since ours is a multi-user system, we now proceed to find out what happens if we have a requirement of multiple users and interference therein. And so now we keeping in mind that EB by N naught for a single user is 16 dB, what will or how many users can the system support if we have a EB by N naught plus I naught, that is interference PSD is also specified, and this ratio now required is 10 dB. Secondly, if the user transmitter power, that is every user's transmitter power is reduced by 3 dB, now how many equal power users can share the band? And finally, if EB by N naught tends to infinity, that is almost negligible noise case, then in that case how many or what is the maximum number of equal power users that can share the band. So this is essentially a multi-user CDMA problem where we deal with EB, that is signal to noise plus interference power ratios, and we try and figure out what is the capacity of the system in terms of the number of users supported. So now we first take up the data which is given, and EB by N naught with only one user without interference, convert it to a linear value. We have the bandwidth of the data specified as well as the spread spectrum bandwidth. So as we know, by definition the processing gain which has been seen in a previous class, it has been derived as well, is the ratio of the spread bandwidth to the data bandwidth. So that turns out to be 10 megahertz by 10 kilohertz, which is 30 dB. So we tackle the first part of the problem, and we see that the EB by N naught was found out. So what we do is we take the reciprocal of this term. This is in order to facilitate or for ease of evaluation basically. So as you see, the required EB by N naught plus I naught is given as 10 dB, which is nothing but 10 in the linear scale. Reciprocal of this is 0.1. So we rewrite these terms, and this kind of taking this reciprocal helps us split this term into EB by N naught and EB by I naught. So we already know what is EB by N naught in linear terms, so we substitute it, and the rest of it is just simplification, and using simple mathematics we calculate the EB by I naught ratio. So it turns out that EB, that is the bit energy per bit divided by interference PSD, is given by or is found out to be 11.25 dB. Now how to use it in order to find out the total number of users supported. So what we do is we have already calculated this, and this expression again is quite common, wherein EB by I naught is written in terms of the processing gain and the ratio of the jammer power to the signal power. So let me just quickly elaborate this. GP by J by S. GP, as we already know, is nothing but the chip rate divided by the original bit rate, and J by S, as I said, is the jammer to signal power ratio. So what this basically means is that we have this S can go in the numerator, and RC is nothing but chip rate, that is the rate number of chips per second. So this is nothing but RC is nothing but number of chips per unit time. So essentially in the denominator over here what we get, and this we know is also equal to 1 by Tc. So in the numerator what we get over here is signal power. This is jammer power into Tc, and R, which is nothing but number of bits, that is of the original signal, per second. So this can be per bit, it is 1 by Tb. So this becomes S into Tb. This, as we know, has been equated to Eb by I naught, which is true because S into Tb gives you Eb, and J into Tc, because this is the interferer power multiplied by unit time, this gives you the interference PST. So basically we see that we express Eb by N naught in terms of the processing gain, which in turn is expressed in terms of RC and R, and we are in a position to equate it to the jammer power to signal power ratio. It's easier to evaluate it in terms of dB, so we write this Eb by N naught which we had obtained in the previous slide. So that was 11.25 dB, and the processing gain is already found out to be 30 dB, so that is mentioned here. And now we get the jammer power to signal power ratio to be equal to 18.75 from this expression, and this is equal to 75, which is precisely the number of users that can share the band, provided that we limit our Eb by N naught plus I naught to 10 dB. This is because the numerator we have the total jammer power, and the denominator is the individual signal power. So this much, or this is the margin, this many number of users can be supported, which is basically found out using this ratio, that is the total jammer power, the total interferer power divided by the desired signal power. In the next problem, we have been asked, we have been told that each user's transmit power is reduced by 3 dB. Since noise PSD remains the same, a reduction in user's transmit power results in the user's reduction in user's energy per bit, and so therefore the original value of 16 dB which was specified is now subtracted and by an amount of 3 dB. So the new Eb by N naught ratio is 13 dB. So you can proceed with a similar analysis in order to prove that the jammer to signal ratio now reduces, and so the number of users that can be supported also reduces. This is because of the reduction in the transmit power of the signal. Finally, we have been told that noise power is almost negligible, so Eb by N naught tends to infinity, and we use this expression which we had used previously for part A of the solution, wherein this first term turns out to be 0, and now we straight away get Eb by N naught as 0.1, which once again, following a similar analysis, gives us a jammer to signal power ratio of 100. So the number of users supported has now increased because the Eb by N naught is we are taking the limit as Eb by N naught tends to infinity, which is a good thing, because what we are saying is signal power increases manifold compared to noise power. in which case the number of users supported is more than what is has been found out in part A. So we move on to the third problem. So in this problem we have been told that we have 24 equal power terminals which have to share a common frequency band using a CDMA system. We have been given the rate of data transmission, which is 9.6, and we have to calculate the rate of the chip rate of the PN code, that is RC, and the specification is that the minimum bit error probability should be 10 to the power of -3. Importantly, the system is a direct sequence spread spectrum BPSK system. So this information is crucial because we need to map 10 to the power of -3 probability to this subsequently. An important assumption that the receiver noise is negligible with respect to interference from other users. So proceeding with the problem, what we see is that we invoke the bit error rate probability expression for BPSK, which is in terms of the Q function, and the argument is √2 EB by naught. We have been given the desired value of probability of error, which is 10 to the power of -3. So we see that 10 to the power of -3 corresponds to an argument value which is somewhere close to 3.10, somewhere in this range. This is almost 0.0001, or rather 0.001, I am sorry. So presumably the value is just before this 3.10, an argument of 3.10. So the precise value of x or √2 EB by naught in this case is 3.09, and this can give you the value of EB by naught, which is 4.77. Now actually receiver noise is negligible, so we can, since that is negligible, the only mitigating factor over here is the interference due to other users, which we shall call it or denote it as J0, where J in a sense is for jamming, but this is more of unintentional jamming, just like in the previous problem. So it's nothing but multi-user interference term. So we don't have N0, but what we have is a requirement of EB by this J0 should be equal to 4.77. So we use that in the expression which we used in the previous problem, and we are in a position, as I said, GP can be expressed as RC by RB, or RB sometimes also denoted, because it's a raw bit rate, it's also denoted as R, and that is already specified to be 9.6 kbps. The J by S ratio we know is the number of users that total number of users minus the desired user, so it's m-1. So approximately what we have is RC of 1.05 Mbps. M of course has been specified to be equal to 24. So this problem is pretty simple, and what it does is it gives you an idea of what is the chip rate required provided the probability of error, number of users, and the information rate is specified. So we move on to the last problem. What we see here is we have 11 equal power terminals in a CDMA system, and all these 11 terminals are transmitting to a central node. So there is going to be interference from one user to all other users, that is each user to all other users. So the information rate is 1 kbps, and we have a chip rate of 100 kilochips per second, and we have been asked as to what is the ratio of bit energy, that is EB, to the interference power spectral density ratio, which is I0 at the receiver terminal in this case. Further, what happens if all the users double their output power, and moreover, if the service is to be expanded to a specific number of users, in this case 101 users, then what must be done to the spreading code in order to maintain the EB by I0 ratio. So we see that the processing gain is the chip rate divided by the bit rate, which is 100. We have been told for problem 4a that there are 11 equal power users, so m minus 1 is 10, and we once again use that same equation, EB by I0 is equal to processing gain divided by J by S, which is m minus 1 approximately. So we have 100 divided by 10, and therefore the solution to part A is the ratio is 10, which is also 10 dB. Now in part B, what happens if all the users double their power? If all users double their power, the corresponding energy also doubles. However, since all users have, each user has double the power, the interference power also doubles, because for a given user, signal from all other users is like interference. So since all users have doubled their power, the interference power also naturally doubles, and therefore we see that the EB by I0 ratio remains the same. Finally, just a small change in the original problem, that is, what if now the number of users is given, but the EB by I0 ratio has to be maintained. So we maintain this at 10, and we increase the number of users to 101. So m becomes 101. So the denominator is 100, and the processing gain required now is 1000. So now what has to be done, because 1 kbps is we have fixed the transmit rate at 1 kbps. We originally had a sequence transmitting at 100 kilochips per second, but now we therefore need the code rate to increase, so that we get a ratio of processing gain ratio of 1000. So we need RC also to be increased by an order, that is to 1000 kilochips per second. So this is the new RC, maybe we could call it RC dash, so that the processing gain turns out to be 1000. So friends, this concludes the tutorial series. I hope you enjoyed the problems, and I am sure you will be able to now solve problems, a variety of problems similar to the ones that we have solved in these tutorials. Of course, we had 3 tutorials dealing with numericals, and the remaining tutorials we tried to introduce MATLAB implementation of simple basic spread spectrum systems. I hope you appreciate those codes as well, and the results and the interpretation. I would like to thank you for your patience and your attention.